Hello everyone, it's November the 1st. Alright, new month. First question, surrounded regions. That's a medium one, right? It's surprising. I thought it's Monday. Alright, let's see. Oh, we haven't done this before. 130. Alright, so we're given an n by n matrix containing x and o's. Capture all regions that are four-directionally surrounded by x. A region is captured by flipping all o's into x's in that surrounded region. So how do we do this? Which one is surrounded by? Surrounded region should not be on the border, which means that any o's on the border are not flipped. Any o that is not on the border and it is not connected to an o on the border will be flipped to x. Two cells are connected if they are adjacent cells. Hold on. Capture all regions that are four-directionally surrounded by x. Why do we flip this? This is they're four-directionally. So this is three-directional, but this. Okay, so I say this region is covered. Going down is covered, going left is covered, so the entire region can be flipped. I need more example. I'm gonna read again. Any O that on the border is a no-go because it will never be, but anywhere else inside will be a go, right? Not on the border. And is not connected to an O on the border will be flipped. Yeah, I think that is the case. So the only thing that will not be flipped is something on the border or anything that's connected to the border, because if I'm connected, say if I'm connected here. Yeah, let's do this example again. Do not return anything. Okay, well, I need to return anything. So let's say what we need to turn is the third. I turn this x into an O. I think this one, if I turn this into an O, then the entire thing cannot be turned. Is that right? Output. The entire thing is not turned because this is connected, so this one cannot be turned. So connected, connected, connected. Everything is connected, so nothing can be turned. So what? So we go around the edge to find there are anything that is connected. So once we find it's connected, from there we're gonna search, and we just go, right? We go around the edge. If we find something that's connected, then okay, let's say I know where it's connected, and then we go here. Whenever this one go up, if it's connected, then it will be remaining as this, and this one. So hold on. So if this one, I look up, I look left, I look down. I cannot say. So we have to search from any O that's on the edge, right? So we blah blah blah, we find some O on the edge, and from this position we need to find everything that it has connected to. So we connected, and once it's connected, it's gonna go all the way, right? All the way down. They should all be O's, and then, but how do we know which one can be? That cannot be turned. I might have to label them differently. Alright, I have to label them differently. So like the O that cannot be turned, let's label them another one. So I'll label them another one. And then we'll look around. We'll look this. I'll say this can be turned. You can go DFS or BFS, doesn't matter. So I go just be a DFS, right? So we go looking for directions. Anything that is, return, and looking from here for directions and anything we can turn, right? And then I need to have a scene so we don't go back to the previous one. Well, that's fine. And then we start from here. We're going to traverse everything that's connected to this. So just a BFS, everything that's connected to this. Once we cannot go, oh, shouldn't we also backtracking? Is there a backtracking on this? Well, not really. Not really backtracking. We don't need to backtrack. We just, right, if this one, everybody checked, nothing, then we don't go anymore. So we just return, right? And then this one, we'll check and return every time we return. So now we all check everything on this, and now we keep looking, all right? Keep looking, and then, and then this, and anything that has turned into, let's say it was a pound sign. Everything that's turned into a pound sign means I have checked this already. So if it's pound sign, we don't have to worry. We'll just keep going. Anything that's not a pound sign, then we go. So this one will turn everything that cannot be turned into a pound sign. Then we go again. All the, like row by row, all the pound signs turn into O, and all the O turn into X. Oh, let's try this. 0, it's going to be 1. Oh, I just realized I don't have. Ah, shoot. So we need to make directly first. So it's 20, 21, 11. All right. Do it again. It's going to be 11:01. And this is going to be 01. Okay. 11. All right. I think BFS is easier to write because we have the recursion. Right? We have the recursion to help us. Okay. So DFS, all right? DFS we have position is I and J. I and J, and we don't need to return anything. So what we do is for ni and j in, we also need n and n equals lamboard and lamboard 0, right? So for this in I plus 1j, right? J plus 1, I minus 1 j, and I j minus 1. Alright, so for this, if 0 smaller equal to ni smaller than m and 0 smaller equal to nj smaller than n, yeah, my cat is meowing. If this and board ni and j is not a pound sign, right? That means I should go there, so I can go DFS ni and j. Right, but before I go this, I can do these two here. So whenever I do DFS, right, that's when I turn it into a pound sign, and then I go DFS. DFS, right? And there's no backtracking. We just label everything, and then once we finish going through 4 directions, and then that's it. So that's DFS. Okay. Now what we need to do is just go around the edge. So how do we do that? What can do for j in range n, right? And we say, hi, my cat is very cute. board this if this is equal to a O, right? If it's equal to a O, then we're gonna call DFS 0J, right? That will be the first row. Anything that's an O, we're gonna call this, and then we let it go. And then if board, and we can go to the last one as well. So if board, last one will be n minus 1 J. Right? If that is an O, then we do DFS m minus 1 J as well. So that is first and the last. So we can also do for I in range m, right? So it's a similar thing. Hey, can we like combine these two together? So it's gonna be I 0, right? That's the first column. I'm gonna go I 0, and this will be the last column. Will be n minus 1, right? And then this will be I n minus 1. Can we combine these? I don't know. This is easier. So once this is all done, then we need to go one more time for I in range m, for j in range n, right? And then we say if board ij is equal to a pound, then board ij need to be turned into a this elif. This is equal to O, which means these can be turned. So we're gonna turn those into an X, and if it's X, we let it go. Okay, so this is my solution, and we are going to have. I think we changed this, right? So x0, so I changed by this into a O. Alright, let's try it. So I have 3 test cases. Ooh, that is not right. Oh, look at the first one. What? Ay. Alright, we need to run some test cases locally. This is not going to work. Bummer. Alright, so what we do is okay, so we have, this is the first one, right? This is the second one. This is the third one. Okay, the result of the first one. Expected. So what's the first answer of the first one? Right? Then answer of the second one is just the same. And answer to the third one is also the same. I remember. Okay. So when you say it's gonna be board, no result, but we're just gonna call it board, and then we say if board is equal to answer. Has no attribute because I forgot to change. It should be a solve. Oh, okay. Rest is not defined because there's no rest, it's only board. Alright, so we have big issue. Oh, everything turns into O. What? It has to be a pound sign. Hold on a sec. Let's just take a look at the first one. The first one shall only have 1, right? Oh, I think this is wrong. If the next one is If the next one, what are you doing? If the next one is this, I don't know what I was doing, man. It was pretty dumb. Yeah, there we go. I think I got this one wrong. It's not pound sign, it's O. Memory limit. Wait, what? Are you serious? Are you serious? Too much recursion? Oh, wait. Changed the wrong thing. Yeah. Changed the wrong thing. No, it's equal. What the heck? Come on, man. It's equal. Oh. Okay, so what I think is it possible to combine these together? Yeah, let's not risk. Let's just try it. All right. 486 days. See you tomorrow. Exactly. I think they add a link. They add a link. That's fine. Doesn't matter. 486. Alright, so this is not too hard. Right? It's not too hard. 130. So this is 130. 130. So use the insight is that any O's that are connected to an O on the edge cannot be turned, right? Cannot be turned. Thus, we can search around the edge to find the seeding O that cannot be turned. From there, we use DFS to mark all the O's that cannot be turned. We use a pound sign for this mark. Once we go through all 4 edges, we will have marked all non-turnable O's. Finally, we traverse the entire grid again and turn all the pounds to O and all the O, the turnable O's to X. OMN, where M is the height and N the width of the grid of the board. And this one runs in 136 milliseconds, or a 87%, 83%. So the majority of the solutions are this. Alright, let's go to discussion. Most votes. Oh, somebody pinned it. Who pinned it? Pinned it as today's solution. Interview-friendly recursion. It's the same. Alright, we call it the B, and then if it's this, if C is not equal to this, if C is O, if C is equal to O, turn to X, otherwise turn to O. Yeah, it's the same. mark border, right? So if this, we'll turn to this, and then we'll go to 4 directions. Same idea, same idea. Why is this one so much easier here? Oh, it check. Oh, I don't have to check it here, right? Ah, because I checked it. Oh, it's slightly different, slightly different. So this one, I check if I am O. Then I go to the 4 directions. I make the check here, so it'll be easier to do here. But the overall idea is the same. All right, I think that shall be it. That shall be it. I like this one, right? I like to check here, and then I will go, right? And then I check again. So basically, I am looking before I leap. I shouldn't say look before. It's we both check, right? But for them, they will just call the recursion first and do the check inside recursion. But for me, I will check and then I go to recursion. Right? So make sure every time I enter the recursion, the state is the correct. It's the correct state. So but the idea is the same. Idea is the same. Okay, so I think that's that. We can call this a day and move on to the next one. Yeah, we have time. Let's roll another one. Alright, let's see which one we get. 725. Oh, I've done this before. Oh, on my birthday. Just recently. Split linked list into parts. I don't remember, but I don't want to do it again. The purpose is to make this value as big as possible. So we'll just roll another one. Find valid matrix given row and column sum. Okay, let's try this one. You're given 2 arrays, row sum and column sum of non-negative integers, where row sum I is the sum of the elements in the ith row, column j is the sum of elements on the jth column of a 2D matrix. You do not know the elements, but you do know the sums of each row and a column. Find any matrix of non-negative integers of size row sum dot length times column sum dot length that satisfies this requirement. Return the 2D array representing any matrix that fulfills this requirement. It's guaranteed that at least one will be there. This is an interesting question. So I know the row sum. Let's use the first example, right? And I know it's a 2 by 2, right? So by the size, I already know, and there's no requirement that it's the same. Some rows equals some, of course, and okay. So it's a 2 by 2 matrix. I already know, and I know the row is 3 and 8, column is 4 and 7, right? So we need to find a way to mix it, and then everything has to be non-negative. I think, hold on, isn't this is also DFS, right? So I can say the first, so I know the largest, so it's 3 and 4, right, to start the first one. It has to be smaller than 3 and smaller than 4, smaller than 3. So so the first row, we know all the values in the first row must be smaller than 3. And all the value in the first column needs to be smaller than 4, right? And all the values in the second column to be smaller than 7. But we can find a value. I mean, the smaller the better, right? So let's say we can search for the smallest in a row and a column sum, right? So that will have the most limited. So it's 3. So the first row has the smallest. So everything has to be smaller than 3. So I can just guess the first one is 1. Right? It's fine. We guess the first one is 1. Then the second one has to be 2. Right? And then we go the first column. The first row is done. Now we go first column. It has to be 3. And then the last one has to be 5. And we have it. 1, 2, 3, 5. Okay. Let's try another one. It's 3 by 3. Now it's 3 by 3. First row is 5. Second row is 7. First row is 10. And 8, 6, 8. So again, the smallest is the first row. So we set the first one. I said is 1. Okay. And then after I do that, the first one remaining is the minimum is 4. So I set the second one. I said it's 1, right? And this is where we diverge, because the second one I can be 1, 2, or 3 or 4. 1, 2, 3, 4, right? So the second one, okay. On the third one, I say I'm going to be 3. The first row is done. And then we're going to go for what? The next smallest is 6. So we go to column, the second column. So now we can, again, we said it's going to be 1. And then it'll be 4, right? Once this is done, what is the next one? Well, next one, the remaining, right? So the first column has 7. The third column has 5. And the second row has 6 remaining, and then another 6, so it's a 5. So the third column is the smallest. So again, if it's 5, I say I'm going to do 1, right? And then we'll have to go 4. Now we go the second column. No, the third column. Oh, it's now it's the same. So it's going to be 5, and then 4 plus 4 is 8, so that's going to be a 2. Oh, it works. It works again. If it doesn't work, so we need to go back, right? We need to go back and then we try another value. Okay. I think, but we need to know which one to use, right? Which one to use. Hold on. So we need to know first which row or which column to go for. Okay, so we pick a row or column that currently has the minimal remaining sum. So that is a priority queue, right? So the priority queue is going to be a tuple. The first value is going to be the remaining sum. Oh, it cannot be a tuple. It's going to be a list. The first one is the... it's fine, doesn't matter. It's going to be a tuple. But sum, a list will be easier to handle. So the first one will be the remaining sum, and the second one will be index, right? And the third one, holy moly, we need the third one. Third one will be indicating whether it's row or column, unless we use a complex number. But even if it's a complex number, we still need to check, right, to see if it's a row or column, if it's like the real part or the yeah. So let's just have another one, like say 0. It's a list of 3 values. The third one, 0, will be row, 1 will be column. So now we know which one to go. Once we find that, and we can set the first one, just set it to 1, right? And then we're gonna search again, right? Search again with the same state, and this the first one will be popped again, and then what's the length? 500. 500. So we need to just iterate through and find the first one that has not been filled, and then we just fill it with a value, and then we're gonna call this again, right? And then the first one will be will get in, and then this one will be called, and it'll be filled, and it will be 0. And when if it's 0, we discard it, and then we find the next one. Okay. So each time we'll pop up a row or a column, and we're going to go through every single value in it, find the first one that's empty, turn that into whatever value that we can find. 1, like we always, that's going to be my thing. Like we're always going to turn that into 1. Once I turn that into 1, and then we go to the next one. What would be the best strategy? To turn it into 1, or I mean, it depends, right? Maybe the best strategy is to get half, because 1 will be too extreme, right? Maybe there's a better chance to turn into a half. Okay, let's say I turn into a half, and every time I always try to even out, right? That's the strategy. Always try to even out. So in that case, we'll just fill in one more value, and then we change the value, we push it back in, and then we recursion call it again, and then a new minimum sum row or column will pop out, and we do the exact same thing. If it's possible to record, right, which position, right? If it's possible to record which position has not been filled. Is it possible to know which position has not been filled? I mean, we can do like, then we need a row and column, right? Yeah, we do still have to go through every single thing. $500, maybe it will not time out. We'll see. All right, let's try this one. One more example. So, two rows, right? 2 rows and 3 columns. First row is 9, 14. Second row is 9, and then 6, 9, 8. Again, we find the smallest. So 6 is the smallest, and we want to even it out. So we push 3, right, and then go. Then the remaining is 3, so that's 3 again, and then go. Oh, and every time we do, every single thing needs to be updated. That is tough. How do we update every single thing? Right? You write this is 3, like the first, and then this is no longer 14. This needs to be changed into 13. Oh, how do I change that into 13? I mean, it's possible. I know it's possible. It feels like the same problem I had in Dijkstra, right? Because I put everything into a priority queue, and then the score changes. But then there is a smarter algorithm that does not rely on this. But I just don't remember how that one is done. Right? I need to push everything into it, but then I need to update. I need to update. But I cannot just push back in again. Let me look for Dijkstra. I think I might get some intuition. Which one? Is it Geek for Geek that has the good? Don't remember. I just want to see the implementation. Let's go Python. Probably have to get it a bit larger. I have a graph. Dijkstra. Distance. Count in this minimum distance. Dist y, I'm updating dist y. And then what? Self.v. I in range self.v. What's self.v? Number of vertices. Larger than this plus this y equals this. So I update everybody, right? And then I go back up, and x equals min distance. And then this in range this. If this is this, turn the min distance. Yeah, this I think they just do it again. Maybe there's no way. Maybe that's the only way. I mean, in this case, I need to implement a separate. Man, this is gonna be complicated. I mean, I could just, go through all the rows, go through all the column. I mean, I update them along the way. I go through everything and then just find the minimum. It's 500 plus 500. It's 1,000. Yeah, I mean, it's just 1,000. I mean, it's fine. Maybe it's fine. I mean, worst case scenario, it's 1,000. Or maybe we don't even have to. We just go the first row and then we go the second row, right? Something like that. Like, we don't even have to. Like, we're gonna pick randomly. Yeah, what if we just pick randomly? Like, we don't care about which one is the smallest. We just pick randomly. Not really random. Let's just pick the first row, right? Yeah, let's just pick the first row. See if this one works. So I pick the first row and then I put a 7, right? Because we say we want to even it out. Oh, then I cannot, because the first column is a 6. See, that's the benefit, right? You don't have to consider. Let's say we go first row and then we need a 7, right? But well, not really. So we are at 0, 0, right? So it's the first row and first column. So we pick the smaller between the two, which is 6, and which is the smaller between the two, and we always put half of that. So it's still going to be 3. So we still do 3. Okay. Then what? We pick the first row, and then we pick the first row again. Oh, the difficulty of pick half is, what if I come back, it's not good? Then I know that's too big or too small. Okay, yeah, that's fine. Then what? Then I can just fill the first row. Yeah, I mean, what's stopping us? Let's just fill the first row. So we're gonna update the column sum, right? And then the first row sum is 11, right? So now it's 11. I'm at 0, 2. Now it is 0, 0, 1. And the 0, 1 need 11, and the column is 9. So we pick the smaller 9, and then we divide by 2. 9 divided by 2 is a 4, right? It's a 4. So we put in a 4. Last position. It's a 7. We have to do 7, and it's an 8. So we have to do 7, right? So we have to do 7. If we cannot do it, that means we're gonna go to previously. Okay, I need to know if it's too big or too small. All right. I need to know if it's too big or too small. How should I signal if it's too big or too small? Right? If it's too small, then my current value will be too big. All right? So I need the previous one to be bigger. In the return value, right? In the return, I can signal if I want the previous one to be bigger or to be smaller, which means if the current value it does not fit, right? If the current value does not fit, if the current value, well, it will fit on 1, all right? It will fit on 1, and it only happens at the last position because along the way there's always leeway, right? So the last one, let's say the last one, in order to fit a row, and the value will be too big for the column, right? So I return too big. So that the last one is too big. So for the previous one, I need to get bigger. So to get the last one, okay, that's fine. So now it's going to be 7. So the first row is done. All right. First row is done. But how do I know the first row is done? If we don't know the first row is done, we have to search through the rows. Or search through the columns. Okay, let's say the first row is done, and I first row is done, and I look for the columns for the next row. Well, we'll look for the next row. The row value. So we'll look for the next row. Okay, the next row. Now the next row we start is 9. Nothing changed, right? So we're looking at 0, 1 position. 0, 1. Now it's going to be 3. First column is 3, 9. So we need to take 3 because that is the end. That's the last position. So we have to take 3. What if it's 2? What if we have an issue here? If we have an issue here, then we have unwind. We have to unwind all the way to the first one. Holy guacamole, how do we do that? Right, yeah, if this one is too big, so I need to tell the previous one need to get, yeah, so the previous one need to get, ooh, that is the thing, right? I fill the first row, and I start the second row, and the first one is not good. Like it needs to be. Hold on, will this happen? Will this happen? Not really. I don't think it will happen because when I go to the first column, right? The first column, let's say, needs to be filled, and it will be filled because every time I only put in half. So the first column will be filled, and that value to fill the first column will affect the current row, but the current I haven't started yet. So I don't think it will happen, right? So it's going to 3. Now the second column, we need 5, and the second row, we need 6. 5 and 6, take 5, divided by 2 is 3, so we take 3. Oh shoot, I cannot do that because it's the last one, so it has to take 5. We have to take 5, and 5 is tolerable. Now the last one. The last one, the column requires 1, and the row requires 1, and we are good. Maybe this one is working. Like we don't have to waste our time finding the smallest. We just go with the flow. I'm gonna give it a shot. I'm not really confident in this one. 1605. So 1605. All right. Let's try this. Yeah, nothing like too fancy. There's no fancy data structures. I could, but I don't decide not to. So row sum. So res is going to be 0, right? Times. Let's just do mn equals len row sum and len column sum, right? And this can times m. No, times n. And the whole thing for underscoring range m. So that is our result. Now we're gonna go DFS. Alright, so def DFS. What do we know? We need to know the row index. So we're gonna go row by row. Like no matter what, we go row by row. So row index and row index, column index, I and j. Yeah, so we do need I and j, right? So we need I and j. We're not going to return a Boolean value. So if it's too big or too small. Okay, so here we go. We're in ij, right? And then we need to find the smaller between row and columns. So for ij, position ij, right? We need to first check if it's the last one. So we say if it's the last one, if j is the last one, right, then it shall become row sum. It shall become row sum, right? So become row sum. And if that value is too big for the column remaining, that is problematic. So it's be like this: if j is equal to n minus 1, right? It's the last column. So I'm gonna go row. So one by one, the row is actually going to the columns. So that's the last column. Then whatever remaining and the row sum, that's going to be. So we're going to say if row sum I, the remaining of the row sum I, is larger, too big, than column sum on the j, right? If it's this, that means we're too big, right? So we're going to return. Oh, no, return false. Yeah, we need to return false. Yeah, otherwise it's good. Alright? Yeah, so it's return false. False means it's too big. False means it's too big. Right? So what we need to put in there is larger than what is allowed. Then we return false, it's too big. And we say if else, right? Else, which means it's not too big, then we can fill. We say res ij equal to row sum I, right? What equal to row sum I, and then feel like there's a couple of things that we need to handle. Let's just write out the whole logic first. So then ij equals row sum I, because that's the last one, right? Then row sum I equal to 0. Alright, row sum I becomes 0. And then column sum j minus equal to res ij. We're updating this. So after updating, we're going to call DFS, because this row is at the end. So it'll be I plus 1, and we go to 0. Okay? So that's that. And then we say if this is true, then we return true. If this is false, right? If this is false, if this is false, then current is too big. So current need to be bigger. No, current is too small. Current need to be bigger. But I can't. I can't change my current value. So I can't change my current value. I can't because this is the last one. I cannot make change. So what I need to change is I just need to go back and I need to make myself. Now is a false coming to me is just saying I am too big. No, it's like something downstream is too big, so everybody up need to be smaller. Yeah, if this one is too, then hold up. No, I need to return. I need to return, like, who is the culprit, right? Who is the culprit? So it's not a Boolean value. Who is the culprit? And how do we know we have succeeded? Well, the last one, and this one, I need to return a list. I need to return a culprit. I need to know who is the culprit. So if I return to there, no, I can't. I cannot. I have to rewind one by one. Right? I have to rewind one by one until we reach the culprit. What we're going to do when we reach the culprit? It'll be easier, right? It'll be easier if we can have a state 500 by 500 and copy this thing every single time. Will be, what if we copy a thing? Like the difficulty I have now is if I find something that's wrong, right? If I find something that's wrong, I will know. If it's the column-wise, then it will be just the previous one, right? So I just return, and then we can unwind the previous, everything's fine. But if it's the problem on the column, now we need to unwind all the way, right? All the way down. We unwind all the way down to that column, like the previous row. And if we have a long row, we have just unwind until that position, and then that position make a change, and then we keep moving. Yeah, so the point is I need to know where to unwind. Unwind into where, right? Okay, so yeah, there are a few things I want to make change. Like if this, right, and I have not changed anything, then I will, yeah, let's return. Yeah, let's return. So the row sum, right? The row sum is I need to do. The row sum is larger than the column sum. Right? The row sum, the remaining row sum, the thing I want to put into this position is larger than this, larger than the column was, right? So that means I am too big. So the previous one needs to get a little bit bigger. Yeah, I don't have. Well, hold on. I can just unwind unless it's like at any position. If the value is too big, right? If the value needs to put in here is too big, it doesn't fit the column, then that just means the current value is too big. So we just unwind it previously to get this one bigger. If this one cannot get bigger, we just keep unwinding. Hold on, maybe it's okay. I don't know. I don't know. I just do this, and yes, and then we say if I equals n minus 1, right? And then if I equals n minus 1, and if column sum I, so the column sum j, right, is the remaining. If the column sum this is too big, larger than row sum I, if that's too big, then we also return false, right? If it's too big, then we return false. Somewhere previously we need to get previous one need to get bigger. So now, once we get these out of the way, which means it's never too big, it's never too small, never too big, then we're going to say the current one will equal to how do we say? Well, I want to look at ij, right? And then we're going to see if the I already did this. That's the thing. Like if ij is already how do I start? I just need a like if it's this and I do a value, I will put it as a row sum. And if I is this, we just need to produce a value, all right? We say if I equals to n minus 1, I produce a value. If I equals n minus 1, produce a value. When we do ij, it will always be a new value. Okay, how about this? Right, this is like a sentinel, right? So if this, I'll turn res ij, because that will be the row sum, right? That will be the row sum I, and then because it's going row by row, so it will always be a new row. And now we say if it's a column, and then we need to check. We say if res ij is smaller than 0, that means it's a new column. I have not filled it yet. In that case, right? In that case, it's a new column. Yeah, it's a new one. It's a new one. Then res ij, right, will equal to column sum j, right? Column sum j. I haven't done it before. Then will be column sum j. Otherwise, if it has been filled, right? If it has been filled, else. If res ij has been filled, that means we have filled n minus 1 already. J equals n minus 1 filled already. But it's also happening. That's the last cell, right? That is the last cell. This is the last cell. So in this case, we are at the last cell. We just need to see, right? Because I put down res as row sum, and we just need to see. We're going to return, right? We're going to return to see if the column sum j, because it has to be the column sum j, if that is equal to res ij. If it is equal, then we failed, right? Otherwise, I mean, we can do this, larger equal to, then we return. All right, otherwise, we set this. Right? The last cell. If it's not, that means something previous needs to change. The previous needs to get bigger, right? Because if they're not equal, it just means the previous one is not good. Okay, so this is the current case. All right, so now we need to check. After all these, we need to check. We say if res ij is smaller than 0. All right, then we need to do the current row ij. So this one has to be the current sum, the minimum of the current sum. So this is going to be the minimum of row sum I and column sum j, minimum of the two, then divided by 2, right? So that's the current thing. Yes, once we have that, so rest is set. Then we need to update the row sum. So we can say row sum I or minus equal to res ij, right? And then row sum, no, column sum j minus equal to, oh, we always have it, right? So update row sum I and column sum j. And once we update them, we're gonna go DFS, right? So DFS, we always go to the next one, right? So it's going to be if j is smaller than n minus 1, if j is smaller than n minus 1, then we go to this, else j equal to, then we go to I plus 1, 0, and this will just be I and j plus 1, right? J plus 1. Okay, and then if this one returns true, which just this one's true, that means we found it, so we just keep return true, and this one will return true as well. But if it does not return true, right? If it does not return true, well, if it does not return true, that means something is bad, right? Something is bad. Then what? It returns false. Alright, so come back to me. So I need to make change, right? I need to make change. What type of change? So I need to be bigger, alright? I need to be bigger. So how do I be bigger? I just, instead of going this, so I have current res, so bigger will be we'll go the maximum of these two, and we'll pick a new one, right? We'll pick a new one. So I already done this, right? So I need to restore them. Yeah, I think let's do this. If it's true and it's true, because the response is the same, right? So I think I can do this. If this and this, right? Or j equals n minus 1 and DFS I plus 1, 0. Right, so these are two conditions. I either go this route, and if it is false, and I go this route, but If this one's false, then this one will be false. So this whole thing will be false. But if this one's false, I go here. This is true. I go. So if this one is good, then we always return true. Otherwise, I need to change. How do I change? I say, so first of all, I need to restore these two, right? So I need to restore these two back to the original, and then I need to pick a new. I need to pick a new and go again. So isn't this has to be a while loop, right? Because I go again and I come back and I change again, right? And if all of my is exhausted, then I return false, and the previous one need to change. Okay, so it's gonna be a while loop. So while this, while what? While this is false, all this is false. So while not this or not this. All right. While, hold on, this is 0. So while this is false, hold on, no. Oh, what is the So if this is true, either one of these true, we need to break out. All right. Either one of these is true, we need to break out. While this is true, so either this is false or this is false. But if this is false, I need to go to this one. Too complicated to handle in here. That's I'm just gonna go while true. And we say if, yeah, this is easier. If this or this, right? If this is true, or this is true, any one of this is true, then return true. Otherwise, we are going to restore, right? And then after we restore them, I'm going to pick a new result. How do we pick a new result? Always I want to be bigger. So I say res ij going to equal to res ij, so the current ij, right, and plus the maximum of row sum I and a column sum j, maximum of these two, and then divided by 2, right, and then divide by 2. So I pick a bigger one, and after I pick a bigger one, I'm going to do this again, updating, right? So update and go back up until a time where I am already, because every time I do this, right, current plus the maximum one and then divided by 2, and if the 2 is the same, like if it's the same, then there's no way. So I'm going to say pre equals to what I have, and then all this is going to be plus equal to pre, and then I'm going to say current is equal to this, all right? Current is equal to this, and this is going to be pre, and then we say if current is larger than pre, then this is equal to current I can reduce yeah, let's just do this. everybody equals current, and then we'll keep going, right? Else, if current equals pre, that means we done, right? We cannot do any more. Then we are going to we can just return false. I can return false. Else we can return false, but I want to turn this current one because I already restored it, right? And with the current one turn into -1 and return false. Okay, so I have a pre, and I don't need to do this one more time. I just do this equals this. I say if current, we don't need the current. If this is larger than pre, right? So the current is larger than pre, so it's good. I remove this and go again. But if it's not good, I'll turn myself into -1, means I haven't tested yet, and I return false. So we throw the ball to the previous one. So that's DFS. And when I go DFS, we'll start from 0, 0, right? We'll start from 0, 0, and we just return this, right? All right. Oh, this is interesting to see if we get this. So first one we say 38, right? 3847 can give us, oh, how do we don't know, right? We don't know. I don't have a, because it's any one. Yeah, we can still do. We can still do, but there's no solution for me. And everything has to be, yeah, that's just 10, right? 8, 6, 8. Second test case. Third test case is 14. 9. And 6, 9, 8. All right. Next one is 1, 0, 1. Last one, they give us an edge case, 0 and 0, right? The goal is not to be correct, like to get it. The goal is to get a thing, and then we need to compute its row sum, column sum, right? So res equals to, this is what? Restore matrix row sum, column sum, right? So once we get it, when you say R res row sum is equal to what? Sum row for row in res, right? And a res column sum. Yeah, res column sum is res column sum equal to sum column for column in. Now this is the same. I think what we need to do is we need to zip it, right? Zip res. So we do this and we zip res, and then we call column. Then that will be the column, right? And what we want is if res row sum is equal to row sum and res column sum equal to column sum, then we pass. Otherwise, we fail, and we need to print the rest. We don't have to print the answer. There's no answer. Here we go. Ugh, what the heck? We fail every single one. What? Alright, that is pretty bad. So the first, oh my god, the result. So the first one, what I get is 1, 2, 3, 5. No, that is correct. That is correct. I think probably here is wrong. Hold on, let me think again. We deconstruct it and we zip it, right? So we zip it and it should be, wait, what is the column sum? Hold a sec. Let's do res row sum and res column sum. I want to see. Three, 8, 4, 7. It is correct. Why these are not the... Huh? What the hell? A false. Wait. Oh. 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 Oh, I know. We need to do this. Answer row sum. Alright, row sum. I'm gonna copy it. Answer column sum. Because it's not it has side effect, right? What's the called? It's not function. Right? It's not pure. It's not pure. Yeah, it's not pure. We're changing. That's why these are not right. There we go. All right. Let's see if this effort bear fruit. All right. Let's see. Pre is not defined. Oh. What? All right. Let's add this to it. And this is the first case where we will have to... Wait. I cannot have negative value. What the heck? Oh, shoot. If it's negative value, that means it's too big. When you get smaller, Okay, so if this is larger, right, because this is the last one I'm going to put in. If this is larger than what is allowed, then I return, this should be an integer. So I want to return signals, right? So return 1 means it's too big, right? And then we say if row sum I is smaller than 0, right? If it's smaller than 0, that means row sum I at this position, it's smaller than 0. It should be like any point that's smaller than 0 we need to address, because at this point, like any point, if row sum I is smaller than 0. Hold on, let me think. Pre, so restore the pre, and then, yeah, because I'm using the maximum, I shall not use the maximum. Hold on. I shall not let that situation happen, alright? Because I'm using the maximum. No, that is that has to be the minimum, because I cannot go be bigger than the minimum. What the heck? This is even more wrong. Oh, this I'm saying is not possible. What? What? What the actual heck? Alright, so the pre is the minimum of these two divided by 2, right? Okay, and then I say it's the previous value and the minimum value, minimum between these two, divided by 2. Yeah, the minimum, because initially is the minimum's a half, and now it's a half and a minimal in between. And that's the pre and this, right? And I say if the new result is larger than pre, well, a new result is larger than pre. Hold on. You might want to plus 1. Okay, again, let me think again. So we have the minimum value, right? We divide by 2. That is fine. Right? Minimum value divided by 2. And if it fails, right? If it fails at coming back, I want this one and this one divided by 2 again. And shouldn't we say pre plus 1? How about we do pre plus 1? Right? How about we do pre plus 1? Because what happens is, in this case, I'll never get to the minimum. But if we do pre plus 1, then we will be able to get to the minimum. There we go. That is correct. Okay, so need to use plus 1 to need to find the midpoint, right, between pre plus 1 and minimum, row sum, column sum. Pre plus 1 is important, right, because without it we will never increment towards main row sum, column sum. Okay. All right. Shot number 2. Try it again. Come on. Don't tell me time's out. Oh, shoot. How many did we pass? We passed half. It's no good. This is no good. TLE. 52 passed 52 out of 84 test cases. I need to be smarter. What if we copy? Right? What if we copy? I mean, what I think is just something is wrong and we just keep rolling back. and like keep rolling back, and it's all not gonna work. Hold on, I'm going back. I'm gonna be back. But make a copy 500 by 500. That is expensive. I feel that is expensive. But although that is expensive, what we don't have to worry about is the rolling back, right? Because we can immediately go to the culprit, right? So we immediately go to the culprit and then handle from there. Yeah, we'll just keep passing the rest. So every time we got a grid, it's the new grid, right? That one we'll copy it when we pass it to the new one. But let's say if it's too big, I rewind. I mean, I can rewind vertically or I can rewind horizontally if you use copy. I'm gonna copy this. That's curious. Oh, it does take a long time. Maybe we do have to. Maybe we do have to use priority queue. Alright, let's go for the hint. Oh, look at that. It's the smallest. Alright, it is smallest. So we have to go back to our original, very beginning. I don't count this as using a hint, but we do use the smallest. Yeah, because smallest, if you think about it, smallest is easier to handle. But I am not going to use a priority queue because I think that is too much. All right, I think that's too much. Okay, let's try it again. I have this idea, so I'm just gonna be like this. So DFS. So every time we're gonna look for the smallest, right? So look for the smallest, and then we fill that specific position. Look for the smallest, so we know the smallest row, smallest column, and then we just walk through it and put into the specific value. And every time we always do that, put in a specific value, and let's try it. So we we actually don't know I and j, right? We don't know I and j. We don't know I and j. All we know is we need to find the smallest. Okay, but the smallest that is not 0, right? The smallest that's not 0. So in this case, we don't even passing anything. So let's say how do I know? The smallest row that's not 0 and the smallest column that's not 0. So row I, right, I equals 0. I min r, right, equals row sum I. Hold on, that's, well, it could be 0. It could be 0. Math.inf, that will be the simplest import. Math. Alright, so I minus 1. Alright, I would say for Ri, Rs in enumerate row sum. If Rs is larger than 0 and we can go 0 smaller than Rs, smaller than min R, and min R equals Rs, and oh, what the heck, I equals to Ri, right? And then we do exactly the same. We do exactly the same with J. So min column, and then it's going to be column I, car, and then this is going to be column, and then CS smaller to column, and column equals to column, J equals column J. Alright, column J. That's column sum. This is column J, right? So once we go through this, if I smaller than 0 and j is smaller than 0, which means we did not find any, that return true, then we're good. Alright, are we good? Boolean, are we good? Otherwise, aleph, if aleph, if I is smaller than 0 and if j is larger than 0, hold on. So I also need to find the minimum of these two, right? Oh, these will be math.inf. So it's going to be if min r is smaller than min c, right? Then we're going to do row, right? We're going to next to fill is a row. Else, right, just one. Next to fill is column. Okay, so next to fill is row. So minimum R is smaller. So we're gonna go I, right? We're gonna go I. How do we do I? We're just gonna go for Ri in range and with fill I is actually is J, so column J, right? And then we say if res I, right, Cj is smaller than 0, it hasn't been filled, then this one will fill it with what? With the entirety? Like with half, right? But how do I know if this is the last one? Yeah. How do I know if this is the last one? Because I'm just filling one value. I'm going to go through the entire thing and find. I'm going to find how many, right? And find how many is -1. So that's how I know how many I need to fill. So I can fill it, and then I'm going to go again, right? But we can't just like set it to 0. Maybe we can set everything to 0. Hold on. What if I do set it to 0? What's gonna happen? And everything will be 0. What are you saying? What I'm saying is, hold on. What I'm saying is, yeah, I'm gonna run some experiment. 3, 8. No, it's 5, 7, 10, 8, 6, 8. We set everything as 0 to start with, right? And then smallest is 5. So I just pick the first one as 5. Right? And then that's done. And then the next one is 6. So I cannot go the first one, so I go this one, 6. So this one is done. Next one is 1. So I say this one will be 1. This one's done. Right? Next one is 3. So this one will be 3. This one's done. And next is 8 is 5. So we're going to do 5. Oh, we cannot do 5 here, so we do 5 here. And then 5 is. Wait, what? It's 8. Yeah. Oh, I think I know. Yeah, this will produce exactly the same as the result. Hold on. So we just do 0. But what if 0 doesn't work? Well, if 0 doesn't work, then we... Well, what if 0 doesn't work? If 0 doesn't work, then... You know what? It says it must work. I think 0 might work. If 0 doesn't work, like if it doesn't work, then what? Don't know. I think it will work. How about that? What's the proof that if you set it to 0 will work? Well, because it say there gotta be a result. So I think if there is some result, maybe we can prove it, then the 0 will definitely work. So let's say if we have a non-zero result, right? We can always reduce 1 to 0, right? We put it in here, and then everything that's coming in here, we're gonna reduce on this, and then put in here. So it's definitely possible for at least for 1 to start with 0. Okay, let's try 0. So we do find blah and blah, and I'm going to fill the row. So the first one that is 0, right? We say for this, if this is 0, right? And column sum, right? And a column sum at a CJ, column sum at a CJ is larger or equal to the minimum row value, right? The minimum row value. If that is the case, right? If that is the case, then res I CJ is going to be minimum R, right? And what? And I'm going to column, so column sum CJ to the minus equal to min R, right? And then row sum I, right, minus equal to min R as well, which is just turned into 0, right? So if this, and then DFS. All right. So if it's not possible, I don't know. We'll see if it's not possible. If not possible, then we just if it's not possible, we go DFS, right? If DFS is false, and we just pick another position, yeah, that's fine. So we're gonna say if DFS, then we return true, right? If it's not, we are just going to backtrack back to 0, plus equal, right? And then this will just go back. We'll look for the next one, right? We'll look for the next one. And if the entire thing, now we're going to return false, right? Else, we're going to fill the column. So it'll be exact the same code, but just change a little bit. So this is going to be row I, right? Because we're filling a column. And then we're going to say row I j is equal to 0, and this is the row sum row I is larger or equal to minimum column. Then this, right? This will equal to minimum column, and then column j. We'll reduce this. Row sum ri will be this, BFS. Otherwise, the whole thing, this one back to 0. This one gonna be min r, no, min column, plus equal to, and plus equal to. I also return false, right? Which we don't have to. We can just do it here. If this, either one, cannot do, and return false. And the remaining is not necessary. Alright, so solution 2. Okay, try it. None type is not iterable. Where? Line 109. Oh, God, did not return. Jesus, DFS. Oh my God. Return res. Oh yes, this is the one. I think this is the one. Come on. Show me something. Show me something. Yes. Yes. Got it. Alright, so I did check the hint, but it was the same idea as I had previously. So previously I was thinking about going with the smallest row or column sum first. But later I decided to not follow through, because perhaps not checking the min would save us some runtime. Unfortunately, it was not working. It did not work. It did not work. Thus, with the confirmation, confirmation from the hint, I went back to checking the min row or column sum first. Now, I did not use a priority queue for this, because there is a need to update elements in the priority queue. It is not impossible, but my current implementation of that requires the creation of a custom object, a custom object to handle this, and I don't like it, and I don't feel it. I don't like it. Thus, I simply just go through the entire row sum and column sum to find the min, since the maximum length of these two arrays are 500. Is 500. On to find min might be tolerable. So after the min is determined, I simply throw the min to the corresponding row or column, corresponding first empty spot in the row or column. This leaves the remaining row or column 0. If this scheme doesn't work, we will backtrack and try another spot to throw in the min, or to throw in the min. Now, I don't have a full proof, but I think, given that a solution must exist, we can always manipulate the solution in such a way that some row or column can be rendered all 0 except for one of them, and that's the basis, right? The runtime, I have no idea what the runtime is. Yeah, whatever the runtime, no idea about the runtime, about the time complexity. I mean, the O(n) squared, right? It's like the best case. The best case scenario is O(n) squared. Actually, O(m) n mn. I'm just saying this should be O(m) squared n squared. Right, O(m) squared n squared. It runs in 1132. 52. Does this count as using the hint? Ah, that's a debate. So we had the same idea. Let's take a look at the discussion. Easy and concise with proof. Proof. Oh my goodness. Oh my goodness. I am completely blown away. What the heck is this? But you need proof, right? Oh, this one is the one failed. Backtracking. Alright. What is this? The greedy pick. So just take as much as possible. We take the min and update. We'll clear either this or this. Either in the end. It's guaranteed that at least one matrix that fulfills requirement. In the end, row I larger than 0, column j larger than 0. Oh, wait, what? Aij will clear either row I or column j. Yes. That means row I will equal to 0 and column j equal to 0 at the end. Yeah, for sure. And the sum always valid. In the end, if row I larger than 0 and column j larger than 0. Then Aij clear neither of them based on 1. It's impossible. So either some row equals 0, some column equals 2. That's what we find right now. I don't understand what you're saying. But I know it just go in and then we just pick the minimum along the way. Okay, so we pick the minimum along the way. That's greedy, yes, that's greedy. And you say if it's possible, Aij either clear. What do you mean by clear? Make them 0? I mean, in the end, everything will be 0. Right? In the end, everything will be 0. And sum this and sum this will always valid. Yeah, that's also true. And in the end, if something is not 0, like in the end, some row and j, like they're not the same. I think that is the case, right? If they're not the same, then we cannot clear. Yeah, I need help. I don't think this is a good explanation. In the end, both row and column are clear, so it's solved. They're always decremented by the same amount. Okay. it's enough to check that the row sum is all 0 at the end. Now, for each row I and each j, decremented by either this or this. If it's the latter, we're happy. We know that row sum will be 0 at the end. If it's the former for every j, after looping through the entire row sum I is decremented by some column, but at the beginning of the row, it was guaranteed that sum this equals sum this larger than so. Oh, his words are very valuable, huh? Only like one answer. I still don't understand. Alright, for every cell, the value in it is constrained by the values in the row. Okay, that's good. The value is constrained by the minimum of these two. That's good. Yeah, I understand that. What if we really pick the largest value out of the possible values each time? Picking the largest value possible, corresponding picking the minimum. Since total equals total, initially we had the equation that this blah 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 equals this blah blah blah. Since we use 3 as a value for the current cell, that becomes this equals this, which follows from the equation earlier. We haven't broken anything. The total still holds. In this manner, for every cell, we can continue to choose the minimum value, which will keep on decrementing a value in the total. Total will still be above, or decompose into just a single value, in which case we will just put a value. I think I gradually started to find it. Not breaking the equation. Yes, that's the key. So every time, if I pick the smallest, right? If every time I pick the smallest, then the entire state stay the same. I pick the smallest, total rows, total columns, they're all equal to 0. No, they're all the same. And if every time I pick the smallest, it's fine. The rows will decrement the same, column decremented the same. So every time row and column will decrement exactly the same, right? Exactly the same. And if we do that after each time, then the entire board, the state remains the same. Because it also says that there will be a solution, right? And every time I take the smallest, it remains the same. So I take another smallest, remain the same. Take another smallest, remain the same. So at the end, at the very end, because during the entire time, row sum and column sum always stay the same. So in the last cell, the row sum and column sum stay the same. Woo! What a journey! Yeah, oh, look at this. Oh, look at this. So complicated. Lesson 3 from Lee 215. Man, he is just so good. All right. Yeah, I don't like Lee's proof. So here is my understanding. Here's my understanding. We can pick the smallest of. We can pick the smallest of each row sum of row sum I and column sum j for each ij, for each res ij, right? Because after the pick, we also decrement same value from row sum I and column sum j. This means some row sum I, right, some row sum and equals to some column sum is preserved after each operation, right? Then after m times n minus 1 operation, which means we are now at the last position, right? We're now we are at res m minus 1, n minus 1. This still holds. Still holds. Since we are at the end, there must be the only row sum and column sum, right, that might not be 0 are row sum n minus 1 and column sum n minus 1. Right, that's the only possibility because everything else we already remove it. So the last one, so that's the only possibility, and then they're not 0. And not 0 on this. Thus we can see that these two are the same. So this equals to column sum. In other words, we have solved it. Right? In other words, we can pick row sum n minus 1 or column sum n minus 1, and the matrix will be solved. Yeah, it's just because we're maintaining the state that a sum and a sum are equal. So at the end, these sum will always be equal. So that's why we can do this. Oh, what a smart! That's a very smart, greedy. So it's easy for I in range M, right? We'll just fill every single one. For J in range N, we're going to say res ij, right, equals minimum row sum I and column sum j. And then row sum I minus equal to res ij, column sum j minus equal res ij. And then return res. Once you break it down, this is so much simpler. So much simpler. Greedy. Alright, this will be the last submission. And then I'm going to call it a day. Oh, it took a longer today. Oh, it's just slower. Huh, doesn't matter. Doesn't matter. Because the two are actually same because I am taking the smallest every single time. So the runtime is the same. The runtime is the same runtime, but just much easier. All right, I want to comment on this. Okay, the key insight in the proof is that row sum equals to sum column sum is preserved after each operation. Therefore, when we arrive at the last position, there at the last position, this, right? At the last position, there, if the, how should I say it? This and the fact that at most one value in row sum and one value in column sum is not zero. One value in this and one value in this are not zero, indicate that row sum, that the only let me do this here, and the fact that the only values that might not be zero are row sum n minus 1, right, and column sum n minus 1, indicate that these two are the same. This equals, right, equals this. Hence the matrix can be resolved via greedy. At the last position, this equals this, and the fact that the only value that might not be zero are this. Let me edit. I want to say since this and we can conclude that this equals this. There you go. All right. That's a good one. That's a very good one. I'll see you guys tomorrow. Adios.